Grab a brush and put a little makeup. Hide the scars and fade away the shake up. Why'd you leave the keys up on the table? Here you go, create another fable. Grab a brush and put a little makeup. Hide the scars and fade away the shake up. Why'd you leave the keys up on the table? I don't think you trust in my self-righteous suicide. Grab a brush and put a little makeup. Hide the scars and fade away the shake up. Why'd you leave the keys upon the table? Here you go, create another fable. Grab a brush and put a little makeup. Hide the scars and fade away the shake up. Why'd you leave the keys upon the table? I don't think you trust in my self-righteous suicide.
Hello YouTube, this is Brian and this is my fourth video, and today we're going to talk about the functional equation, as you can see right here. Boom. Let's just get into it. Today I'm gonna introduce two functions here. One is one that we are already familiar with, that is the zeta function. We're all familiar with it. You wouldn't be here if you haven't looked into it yourself. We all know it. We all know that we're obsessed with it. We're all trying to find its secrets. And today I'm going to make the case, or start to make the case, that there's an actually a function that is greater than the zeta function. Kind of its parent function, and that is the epsilon function. I just went ahead and coined that term today. I chose epsilon because it's an E, and you know there's terms with E's in the epsilon function. These all have E's in it, and also it's a crazy function. Like, put in 0 for x. Let x equal to 0. What do you get? Well, this turns into a 1. 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 What do you think that's going to equal? It actually equals zeta of 0. So there's a crazy connection going on, as we will see by the next slide. Also, just why the name works so well, small epsilon is used for things that are tiny in analysis. Big epsilon just seems to fit for this function because it just deals with infinity. So let's go on to the next slide here. The zeta function is a fractional derivative of the epsilon function at 0. So this is the deep connection that I'm talking about, and why we should all just kind of realize that the future of math, I'm going to tell you right now, the future of math is going to be fractional calculus, complex analysis, number theory, all that shit, all combined into one. Oh, and also add functional analysis, linear algebra, matrix algebra. All these things can be just combined into one, and this is where my channel is going. You will see in the next couple videos me doing a matrix representation of these functions, and it's gonna get fucking nuts, okay? This is not a channel for people who just want math that was made for a mass audience. This is for people who know what they're doing, kind of. I'm not saying I know what I'm doing, but who can navigate through these crazy, mind-bending hallways of hell that these numbers live in. I mean, it's gonna get crazy. So I'm warning you, this is gonna jump a couple levels from my previous videos. So let's go on. The different integral operator for the zeta function. So we can write zeta as the derivative of epsilon, of course. These are all equivalent. And we can put this in a contour integral form. This is Cauchy's integral formula, but we pushed it to have S be any complex number except -1. Yes, except -1, because of course the zeta function has a pole there. But that's the main point of fractional complex analysis, is that you can take complex derivatives of functions like the epsilon function and you get the zeta function. Okay? So the basic, so let's go back a slide. Where the basic format of this slide presentation is, we start with an equation up here, we do some work, and we get down here. Okay, I'm sorry with the bad arrows here, but that's going to be the basic format of my slides. So, and then that bottom will become the top. So we have this contour integral. We're just going to simplify by noticing that this is just 0. So we can just collapse that parentheses on itself, and we can also put the x on top. So look at, here we go. That's all I really did, is I just put the x on top. You have to take the negative of the 1 minus s term, which is s minus 1, and I got rid of the 0. Easy peasy, easy peasy. Almost said something else there. And on here, so we want to use that formula for the geometric series, you know, because this right here looks like a geometric series, but we want to ensure that that the terms are always less than 1, just so everything is just kosher. You know what I'm saying? We just want to make sure that, you know, we don't break any rules and make all those people in the universities all angry. You know what I'm saying? So let's just do some tricks, okay? In this one, we're just gonna substitute for every x a negative x. Look at it, right? I'm gonna put it right here. I'm gonna put it right here. I'm gonna put it right here. That's all I did here. And also, when you do that, I also need to make a note of the contour that we're using. Let's just go back a slide here. The contour we're using is the Hankel contour, which is this thing right here. And the reason why we're using that is will be useful. Will be shown to be useful later. For right now, just know that. Oh, there should be a little circle right here. Sorry, guys. Just know that this contour can be broken up into two integrals, this one and this one, and it can also be broken up into this way and shown that you can derive this without using fractional calculus, and that's how Riemann did it and how others do it. Just know that this is the case. We'll get into this later. And as we go back here and we make the substitution for all the x's into negative x's, you must also do that for the integrals, for the interval, for the integral. That's so crazy. You got to do it here and here and here and here, and you'll see that the contours change. Look at now, this is negative and this is negative, and now the contour is over here. Just a little something to pay attention to. So yeah. Anyways, I'm going to slide 5 here. So now that we made all these substitutions for x, we now have a geometric series that will be friendly to us. And you can go on Wikipedia, look at the formula for the geometric series. I know it by heart because it's just the best relation ever. One of them. And we just have this. It just gives us this. Right there. Pretty cool. All right, slide 6. So let's just go back. Now that we made that substitution for x, which allowed us to make use of the geometric series, and we got rid of that summation formula, and we got a nice little guy right here that seems very workable. Let's just go back to the original contour, the Hankel contour. So let's just make everything. Let's just go from negative x back to x. Okay, and that's what we did right here. That's what we did right here. That's what we did right here. And that's what we did right here. See? I changed all these x's up here back into positives. Isn't that great? And some of you might be saying, hey, Bright Dog, what is this -1 doing? What is that -1 doing? Huh? Well, that's a great question. See, I did some algebra in my head because I don't want to make another goddamn slide. I'm trying to keep these slides to a minimum. And I just, it would have been written like this, 1 minus e to the x on the bottom. It would have been like that on the bottom here if I didn't do that. So I went ahead and switched these guys. See, right here, I just went ahead and switched them to switcheroo. Now the e to the x is in front and the -1 is in the back. And I just kind of brought out a -1. Okay? Slide 7. And now that we have this nice, beautiful contour integral, shit's about to get crazy. We're about to go into the world of logs. We're going to enter a portal into the world of logs. Prepare to get nuts. Okay? So what we're going to do here is we're going to transform all x's into log x, okay? And hold on, I need to take a drink here. This is hard work, all this speaking into a microphone and creating these goddamn PowerPoints. It's a lot of work. Whew. And I'm sick. Ugh. All right. So we're going to make that transform. We're going to do for all the x's. We're going to do for this one. We're going to do for that one, that one, that one. And what we're left with is that. We all know this is going to turn into an x. We all know that this is going to turn into an x. And this is going to turn into a 1 over x dx. Let's just see what happens here. I guess I was going to wait for that on the next slide. So let's just see here. 1 over x dx. This is just an x. This is just an x. Come on, S Pen. This is good. That's good. And look at, oh. So this will cancel out with this guy. And we're just left with this. Look how beautiful this is simplifying, by the way. Isn't that nice? Also, we had to change our contour. We're in log world now. Substituting x into log x. Now we get these intervals that go from positive to negative infinity. This is how logs work, and it's just wrapping around both the positive and negative infinities here. Oh yeah, by the way, if you guys didn't know, maybe I didn't make this. Hey, stop! If I didn't clarify this, my goddamn dogs. Hey! If I didn't clarify this, these contours are wrapping around infinity. So imagine infinity is right here. They're just going out to infinity and walking around it and then coming back. All right. Pretty crazy. So what about this negative 1 term? As you can see, this is where it gets crazier and crazier. So this negative 1 term, this is what our integral looks like right now, kind of in its basic form. If we just make that negative and reverse the direction that we move around the contour into a clockwise direction, then it gets rid of the negative sign. And also, so now instead of going this way, counterclockwise, now we're going in clockwise direction. And I don't know if you know this, but when you walk on a contour, you always look to your left. You never look to the right, you always look to your left. And so this negative sign being used to reverse the direction of the contour has great implications. Because now we're not looking at the origin anymore, or the real number line. We're looking at everything besides that. So this is how it simplifies. We just got rid of the negative 1, but we've changed the direction of the contour. So just note that. And then on our next slide, we're going to realize that. So now we're starting here. This is our current basic form of our contour integral. And we're going to realize that that there are residues that exist on 2 pi I, 4 pi I, 6 pi I, and also the negatives. So every even integer value times pi I, there are residues that we are going to look at. Because now we're looking to our left, we're looking in this blue region, and what we see is not the origin anymore, but we see that these little residues exist, and I've drawn that here. So you can rewrite this as a sum of these little mini contours, these gamma sub n's. Here's gamma 1, here's gamma 2, here's gamma sub 3. There's also the negative 1. This can be written as a sum of those residues. And you may be wondering why that is. Well, it's because we're in log world, and even the number 1, which I'm writing right down here, is multi-valued. This is equal to n 2 pi I. Okay, where n is any integer, really. E to the 10 pi I is equal to 1. And when that is the case, we get singularities and we get residues. And it'll be more clear here in a second, because what we also need to realize is that we are in Cauchy form. So that's our next slide here, is that we are in Cauchy form. We can go ahead and do the reverse of the fractional version of the Cauchy's integral formula. So let's just do the reverse of that. We go down here. Sorry, I'm a little... God, it's hard talking when you're sick. Whew. We are in Cauchy form, so let's get out of that. And what we have here is we're left with the gamma function of 1 minus s. And we're left with, because that this was just to the first power right here, this is just to the first power. This is just 0. This is the function in question. So this goes right here. Right here. And this is going to be the input of that function. So that goes right here. And we can go ahead and just input this. So let's just go ahead and input this x in. We don't have to take any derivatives, by the way. It's just a straight up function that we're just inserting the x into. And the e and the log will cancel, and we're just left with this. Look how much this is collapsed. This is nuts. It's fucking nuts. So we're just left with the gamma function, and the n 2 pi I to the s minus 1 power. This will collapse even more. First, we got to expand it, though. First of all, we got to fix this index. Because if you remember, if we go back a couple slides, we're on slide 13. Let's go back a couple slides. As you can see by this graph right here, we're doing all the integers except 0. Okay? And you can see that right here. N can be any integer except 0. That's a very crucial point, because now we can, let's go back up to 13, because now we can break these up into two sums. One being all the positive integers and all the negative integers, and we can make these sums the same index, where n is starting at 1. It's a clever little trick there, but a very powerful trick indeed. The next slide, we just break it up into even more parts. So, get the n out, which is n to the s minus 1. We get the 2 pi out, and we can even kind of combine the sums and group them together in a way where the i's are the ones that are kind of doing all the phase work, if that's a good way to put it. So here's all the positive integers are represented there, and here's where all the negative integers were represented. So this is just a way to rewrite this sum. And like I said, for every single one of these slides, it's highly recommended that you pause the video at least and just work it out yourself to see how I got it. Like I said, math is only learned by struggle. There's no other way around it. Literally no other way. So now that we have our little expanded little guy here, well, look at this. This is just the zeta function. Wow. That's crazy. And we're just going to put that as is. This 2 is going to go there, as you can see. And then we're going to put this pi right here. We're just going to separate everything. And then this guy, I'm going to leave this for a little fun project for you guys to do at home. But you can also just go to Wolfram Alpha and just type this in. But I don't want to add another like 4 slides into this presentation because it's getting long enough. But go ahead and do this at home. Okay? Just do it on, in your own leisure. Try to show that this does in fact equal 2 times the sine of pi s over 2. It's pretty interesting. Okay? This is where all the phase information was stored in of this beautiful function, this beautiful functional relationship between the zeta function. So as we go into slide 16, now we have arrived at the functional equation right here. And we also have, it can be written in the terms of this new epsilon function, of course, where derivatives of the epsilon function are being taken. So there's some crazy relationships here. And that's pretty much it. That's pretty much it for the functional equation. So what's coming up on this channel? Today I kind of showed that the zeta function is the negative s fractional derivative of the epsilon function. This has some great implications that we will explore in future videos. And here's one that has been keeping me up at night. Okay? This is what I just recently just kind of thought about lately, this like last week. So what the Cauchy's integral formula does is it's kind of like a program where you put in a function and it will automatically to whatever index you chosen for it, it will find that index of its Taylor series for f and output the constant. So in another way, I have a function f and I'm going to put it that as an input in this mysterious box, Cauchy's integral formula, CIF. And I'm also going to put in a index of what I want in n. And what pops out is f. Oh, we also have to input also a point that we're looking for, like an a. And what pops out is f to the a and the nth derivative of that function. And this is just a constant. This constant exists. This is a constant. Meaning that it already existed as it does, as we all kind of know, in the Taylor series. If f has to be written as a Taylor series, equals some Taylor series, and it contains this constant. And what the Cauchy integral formula does is it automatically takes all these inputs that you put in and pops out from the Taylor series this constant. Which means that since we kind of shown that epsilon has an uncountable amount of these little constants, because I can write one for every complex number in the complex plane except -1, that where are those other ones? Where are the uncountable other complex valued ones? Do those exist in series? Are there uncountable series for this function? I really feel like this is getting into some functional analysis and like some crazy infinite dimensional matrix shit going on. And we're going to explore this in the next couple of videos, so stick with me. Send me a $5 tip on PayPal. I'd really appreciate it and get these videos out faster. Sorry, I had to shill there a little bit. And I mean, what this channel is all about is that we are traveling in the dark, mysterious catacombs of where the numbers lurk. I mean, these numbers are fucking nuts. Okay, I'm sorry I'm cussing. I know this is supposed to be an educational channel, but really it's not. This is a channel that will journey into the abyss. This is where we're going. I don't care about your fucking education. I don't care about my fucking education. I care about going into places where things don't make sense anymore, where reality gets blurred with things that are incomprehensible. This is what this channel is about. It's about losing your mind on trying to figure out the personality of the numbers. This is what this channel is about. Okay? And I can't stress that anymore. If you came here for an education, yeah, you're going to learn some stuff here. But I really want the viewers to come here because they are intrigued and they are dying to know what will happen next, or what are numbers made out of. I mean, has anyone ever asked that question? Is what are numbers made out of? And dog whistles. I've just been hearing this term a lot in the media. You know, it's used in mostly political in political context, but the reason why I'm attracted to these zeta functions and epsilons, infinite sums, is because I feel like humans did not make up math. We're getting a little philosophy here, kids, but humans did not make up math. I'm going to tell you this right now. Call him what you want, but you know, I'll just call him God. He's the one that made up math. And when God shows me something like this, 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 ... is equal to negative 1 over 12. That's a goddamn dog whistle for people like me who are just so intrigued by the wackiness of the numbers. Because if you want to know how the universe works, you got to know how the numbers work. And if there was any final destination for this channel, and this might take years to get there. I'm just doing a little foreshadowing, kids. But if there is any final destination of where this channel will go, then that will be climbing Mount Entropy and conquering it. Because literally, this is what this is all about. You know, when I show this equation to people, they say oh, that doesn't make any sense. How does something that adds up, you know, that gets bigger and bigger and bigger add up to a negative fraction, 1 over 12? Well, that would make sense if these numbers were like masses or like objects. Yeah, that would make sense. They're not masses though. Numbers are information. And I feel like this equation right here is a formula that says something about entropy. I really do. If you want to get philosophical, I believe that if you want to, you know, really know how the universe works, it's really knowing what entropy is and what information is, because that's what I think the world is made out of. If you break everything down to its smallest thing, It's not atoms. It's not strings. It's not, any of this nonsense. It's not quarks. It's information. And that's why I feel like God is sending me a little dog whistle here. Hey, Bright Dog, look at this crazy formula. Why is this? I think this is a formula that says something about entropy. And that's it. That's the end of the video. Send me, a tip at PayPal. I'm gonna try to get this Patreon thing going. Maybe I'll, for a couple bucks a month, we'll do I'll post. You'll have access to my, PowerPoint slides or something. I'd really appreciate the support. You can also send me some Bitcoins. That would be good. That'd be also good. Or just subscribe and like. That's I also appreciate that. So thank you, and that's it. Bye bye.